This is module 27 of econometric modeling. In 26 we started discussing ARMA and ARMA processes. So, we had discussed there primarily moving average processes, that is AMA processes, and we also towards the end started discussing AR processes, that is autoregressive processes. Autoregressive processes of order 1 were probably introduced, and here I am going to continue with the discussion on AR processes further along with ARMA processes. So, we have discussed already, as I have said, that AR1 process. Now, going for a generalization, an ARP process with a constant mu, the conditional mean would be expected value of yt given is equals to mu upon 1 minus phi 1 minus phi 2 and so on up to minus phi p. Just for your reference, that an ARP process would look like yt equals mu plus phi 1 yt minus 1 plus phi p yt minus p plus ut, where ut is a white noise error. So, this has 0 mean and constant variance and no autocorrelation or autocovariances between the error terms. So, given this my ARP process, we can find out that the conditional mean or the unconditional mean is actually, so when the mean is, we go for a calculation of the mean not conditional upon the values, the previous values. If we condition it upon the previous values, then it would look something different, slightly different, but unconditional mean is actually, we take the entire thing, all the lagged values to the left hand side, and this comes to the denominator. Expected value of ut is equals to 0. So, mu divided by 1 minus phi 1 minus phi 2 and up to phi p is our unconditional mean. Okay. The autocovariances and autocorrelation functions can be obtained by solving a set of simultaneous Yule-Walker equations. Yule-Walker equations were introduced in the context of moving average processes, that they are recursive. This is a set of recursive equations. So, that if we have the initial value, that is in the context of moving average, if you have the initial autocorrelation value which is say denoted by T naught, then we can consecutively calculate the rest of the correlations. So, similarly by applying the Yule-Walker equations, we can also calculate the autocorrelations for an ARP process, and this is actually could be obtained from this set of recursive Yule-Walker equations. We call it equation, or the set of equations are called equation 1. So, tau 1 refers to autocorrelation between the first, between say yt and yt minus 1. So, when the lag between the two observation is 1, we denote it by 1, and tau refers to autocorrelation. Similarly, tau 2 would refer to autocorrelation between yt and yt minus 2, right. And similarly, tau p would be autocorrelation between yt and yt minus p. Okay. And that is how actually, given the set of equations, we can actually solve for the values of tau 1, tau 2 to tau p. I will be applying this equation for calculation of tau 1, tau 2 in the coming slides. So, in AR1 models where oscillations occur only when the coefficient is negative, where the autocorrelations switch sign at each successive displacements. We have already discussed AR1 processes, and if you remember, then we discussed that if we have positive coefficient of the AR1 term, then we have monotonically decreasing lags and monotonically decreasing autocorrelations. If we have negative AR1 coefficient, then the decay is actually through oscillations. So, the decay would be like something like this. However, in higher order AR models, the autocorrelations can oscillate with much richer patterns reminiscent of cycles in the more traditional sense. So, if we go for higher lags, we can basically replicate the way business cycles are actually observed. So, the decay will not be very fast and we can probably get closer to the reality, the way we generally observe the series or time series to actually move over a period of time. This occurs when some roots of the autoregressive lag operator polynomial are complex. Consider for example, an AR2 process which is like yt equals 1.5 yt minus 1 minus 0.9 yt minus 2 plus ut. Now, the interesting thing is that this is our lag operator. So, I take yt minus 1 and yt minus 2 to the left hand side, and by applying the lag operator, this is actually my the polynomial in lag operator 1 minus 1.5 L plus 0.9 L square. So, this is the corresponding lag operator polynomial and its two complex conjugate roots are 0.83 plus minus 0.65 I and their inverse are 0.75 plus minus 0.58 I. So, as you remember that we mentioned the condition for stability or the way we defined covariant stationarity that requires the inverse of the root of the polynomial lag operators to lie inside the unit circle. Alternatively, one can say that the roots of the polynomial lag operator should lie outside the unit circle. So, in case here since we from the beginning went with the definition of the inverse of the root lying inside the unit circle, going by that we must have this inverse of the root lying inside the unit circle. Okay. From the set of equation in 1, it can be shown that for an AR2 process, tau 1 is actually could be obtained as phi 1 divided by 1 minus phi 2. Now, you remember that if it is an AR2 process, we have only two coefficients phi 1 and phi 2. Higher coefficients are actually non-existent and that is why we can call them 0. So, setting any higher phi 2 is equals to 0, my equation actually gets truncated here. So, tau 1 is phi 1 plus tau 1 phi 2 and then by rearranging terms by taking this to the left hand side, I would obtain tau 1 as phi 1 divided by 1 minus phi 2. So, this is what is the autocorrelation for an AR1 process, the autocorrelation of the first lag. Using this formula, we can evaluate the autocorrelation function for the process in example. Since the roots are complex, the autocorrelation functions oscillate and because the roots are close to the unit circle, the oscillation actually damps very slowly. This was also shown earlier that even with real roots, if we have the phi or the coefficient very close to 1, then the AR series is actually much more persistent, right. The oscillations are very gradual and similarly if the roots are close to 1, then this oscillation would also be very persistent, the decay would be actually very slow. But there will be decay because the complex roots are expected or should lie within the unit circle. The autocorrelation functions are shown in the following graph. So, this is a graph which basically plots the autocorrelation functions and this is where the displacement here refers to lags and these are autocorrelations. So, you can see that this actually movements is closer, this movement is actually closer to the way we most often or we could observe the business cycle or some of the economic variables to actually move in real life. Okay. Though it is not necessary that the business cycles tend to taper off or they are decaying, but then more persistent oscillations are probably one of the characteristics of many economic series. Now, we talk about partial autocorrelation function. The partial autocorrelation function denoted by tau kk measures the correlation between an observation k period ago and the current observation. So, if we go for simple autocorrelation, this is denoted by tau k and since I am considering partial autocorrelation, so now we are having tau kk as in the subscript. After controlling for observations at intermediate lags, that is all lags less than k, we arrive at this partial autocorrelation function. Okay. So, this implies that it directly connects the current observation with k period lagged observation, and the observations in between are actually not taken into consideration. Alternatively, it measures the correlation between yt and yt minus k after removing effects of yt minus k plus 1, yt minus k plus 2 and so on up to yt minus 1, which essentially implies that all the intermediate terms have been removed, or their impact on the autocorrelation between these two terms are removed. For example, the PACF for lag 3 would measure the correlation between yt and yt minus 3 after controlling for the effects of yt minus 1 and yt minus 2. At lag 1, the autocorrelation and partial autocorrelation coefficients are equal because there are no intermediate lagged effects to eliminate. Thus, tau 1 is equal to tau 1, where tau 1 is the autocorrelation coefficient at lag 1. So, at lag 2 we have lag tau 2. At lag 2 we have the autocorrelation denoted by tau 2 and this is how it is calculated, which is tau 2, that is we consider the autocorrelation between the first current observation and the observation at lag 2 minus tau 1 square, which is basically square of the first autocorrelation 1 minus tau 1 square. Now, how do we arrive at this formula, and for higher order formulas this is actually complex and that is why kept outside the discussion. For higher lags the formula becomes even more complex and hence not included here for further discussion. Note that the sample partial autocorrelations are the estimated parameters of an autoregressive model such that if the fitted regression is yt hat equals beta naught hat plus beta 1 hat yt minus 1 plus beta tau hat yt minus tau, then the sample partial autocorrelation displacement at displacement tau is tau equals beta tau hat. This essentially tells us that why partial autocorrelation functions are important to us, because partial autocorrelation function gives us exactly the estimated parameter from an autoregression model. So, if I go for an autoregressive model of order say tau, so this is an AR tau model and this is the estimated part. So, the initial model would have an UT population error term along with it. Now, when we go for the estimated model, we are only considering yt hat and that is how this is the estimated parameter, all these are estimated parameters. And what these estimated parameters measure? They measure the impact of say the value of y at lag tau on the current observation while we control for all other observations. So, holding other things constant, how yt minus tau impacts y tau is captured by beta tau hat, and this is exactly equal to the partial autocorrelation function between the current observation and the observation at lag tau. So, that is why we say T tau is identically equal to beta tau hat. A correlogram analysis simply means examining the sample autocorrelation and partial autocorrelation functions along with their related diagnostics. So, when we actually I showed you the equation 1 which consisted of a set of Yule-Walker equations. This is my equation 1 which is actually a set of simultaneous Yule-Walker equations. We can call it a correlogram which basically helps us in calculating autocorrelation functions, and similar correlogram we can also have for partial autocorrelation functions, right. So, a correlogram analysis simply means examining the sample autocorrelation, partial autocorrelation functions along with their related diagnostics. Now, I start talking about ARMA processes, alternatively they could be called ARMA processes. By combining the ARP and MAQ models, an ARMA-PQ model is obtained. Such a model states that the current value of some series y depends linearly on its own previous values plus a combination of current and previous values of a white noise error term. The model could be written as phi L y t equals mu plus theta L u t. So, this is simply when we actually bring together AR component and MA component. The name itself suggests that both of these things are brought together, put together to form this model, which is called an ARMA process. So, where phi L is basically the AR part. So, phi L is 1 minus phi 1 L, phi minus phi 2 L square and so on. We are writing in terms of lag operators. Similarly, we have phi p L raised to the power p. All of them are having this negative sign because they were in the right hand side, or they are supposed to be in the right hand side, and we bring them to the left hand side. And this is theta L. Theta L is basically the MA component. So, this is while expanding again, this is in terms of lag operators. So, we have 1 plus theta 1 L plus theta 2 L square and so on up to theta q L raised to the power q. Now, first I wrote it in terms of lag operator, now I am expanding it. So, what I have y t equals mu, which is the constant term, plus the lag operator again brought back to the right hand side, that is, this is the AR components, and then we have the MA components, right. So, this is the MA components. So, this is an ARMA PQ process. P stands for the order of the AR component and Q stands for the order of the MA component. So, if it is like y t equals mu plus phi 1 y t minus 1 plus theta 1 u t minus 1, then this will be an ARMA process of order 1 and 1. Similarly, we can go for ARMA process of order 2, 2, etc. In terms of lag operators, equation 2 can be rewritten as this. So, I actually I am writing equation 3, provided the roots of, in order to prove the covariance stationarity condition or show the covariance stationarity condition for an ARMA process. So, I again write it in its previous format. So, which we have is phi L y t equals theta mu plus theta L u t. Now, this we can write provided the roots of 1 minus phi 1 L minus phi 2 L square, that is the AR lag operator, lie outside the unit circle. Both sides of equation 3 can be divided by this lag operator polynomial of the AR process to obtain this expression, where psi L is basically this thing divided by this thing and C is mu divided by the polynomial lag operator of the AR components. So, polynomial lag operator of the MA components divided by polynomial lag operators of the AR component gives us psi L, and C is the constant term, which is mu divided by the polynomial lag operators of the AR term. Thus, the stationarity condition of an ARMA process depends entirely on the autoregressive parameters and not on the moving average parameters. So, this is important to note that the condition is again with respect to only the autoregressive parameters. The root of the polynomial lag operator related to or associated with the AR component needs to lie outside the unit circle, and we are actually not concerned about what is happening with the roots of the polynomial lag operator of the MA component, right. Okay. So, here again expected value of ut equals to 0, expected value of ut square is equal to sigma square, a constant term, and expected value of ut us equals to 0 for all t not equals to s. The characteristic of an ARMA process will be a combination of those from the autoregressive and moving average process. From equation 2, so this was our equation 2, it can be obtained that the mean of an ARMA series is given by expected value of yt equals to this. This actually can be obtained from equation this equation actually. So, if we go for expected value of yt, then this becomes C because this is constant, and then psi L expected value of ut. Since expected value of ut is equals to 0, what I am left with is simply mu divided by 1 minus phi 1 minus phi 2 up to minus phi p. The autocorrelation function will display combination of behavior derived from the AR and MA parts, but for lags beyond Q, the ACF will simply be identical to the individual ARP model, so that the AR part will dominate in the long run. Because if you remember, when it comes to MA processes, then we have autocorrelations higher than the lag of the MA process, all equal to 0. So, for an MA process, the autocorrelations are available or non-zero only up to the order of the process, while that is not the case with AR processes, and as a result of which autocorrelations will be truncated, for MA processes equal to their orders. As a result of which, when you consider AR MA processes, the AR process having longer term autocorrelations is going to dominate in the long term, and that is why we say that the AR part will dominate in the long term, because MA part is going to have autocorrelations only up to the order of the MA process. Now, we discuss the characteristics of AR, MA and ARMA models. So, this is sort of a comparison between the three models. First of all, for AR processes, we can experience a geometrically decaying ACF or autocorrelation functions. Here ACF refers to autocorrelation functions and PACF refers to partial autocorrelation functions. So, for AR processes, a geometrically decaying ACF is observed, and for MA processes a number of non-zero points of ACF equals to MA order. Alternatively, ACF turns 0 for lags greater than MA order. So, if MA process has only 2 orders, then after 2 lags the ACF is going to be equals to 0. So, it gets truncated at lag 2, while an AR process even with 1 lag will be having a geometrically decaying ACF. And for AR MA process, we will have a geometrically decaying ACF, because in case of ACF the AR model will dominate, right. Now, consider the PACF, that is partial autocorrelation functions. A number of non-zero points of PACF equals to AR order, or PACF turns 0 for lags greater than AR order. So, that was a particular peculiar characteristic of AR processes, that for AR process PACF, that is partial autocorrelation functions, are available only up to the lag of the order, because if I am having an AR process of order 3, then I will be having PACF between the current value and the first one, between the current value and the second lag, and between the current value and the third lag. After third lag there exists nothing. So, we will not have any PACF, but that is not true for MA processes. For MA process we have a geometrically decaying PACF. The reason is that if you remember, an AR1 process can actually be expressed as an MA infinite series, right. And similarly, as a result of which we can say that a geometrically decaying PACF is observed for an MA process. A geometrically decaying PACF will also be observed for AR-MA processes, because here the MA model will dominate. So, as you can see that AR-MA process, since they combine both AR processes and MA processes, so it has the dominating characteristics of AR models sometimes, and it has the dominating characteristics of MA models when it is required or when it comes to calculations of PACF. Now, I will show a diagram where also this similar diagrams have already been shown earlier, but with some examples I can show you the graphical depiction of AR and MA processes. So, this is panel A. Panel A has an MA1 process where we have a positive coefficient of 1 lag or the first lag. So, this shows that this is the autocorrelation at lag 0, and at lag 1 there is this autocorrelation of 0.8, and after that it gets truncated. Now, panel B has an AMA4 process, and again you can see that the first lag is this is at 0. So, this is equal to 1. After that we have minus 0.6, then plus 0.3, then minus 0.5, and then plus 0.5, and so on. This gets truncated here. Now, this is panel C. Panel C has an AR1 process which has a positive coefficient. So, the autocorrelation functions actually decay monotonically, and panel D has autocorrelation function with a negative coefficient, AR1 process with a negative coefficient. So, the autocorrelation functions are persistent and it decays with oscillation. So, whatever we have been discussed so far, that is again shown with some examples graphically. Now, I actually talk about one approach suggested by Box-Jenkins for building ARMA models. Although the existence of ARMA model predates them, Box-Jenkins were the first to approach the task of estimating an ARMA model in a systematic manner. Their approach was a practical and pragmatic one involving 3 steps. So, they suggested 3 steps to follow. First one is identification, the second one is estimation, and the third one is diagnostic checking. These steps are now explained in greater detail one by one. So, talking about step 1, this involves determining the order of the model required to capture the dynamic features of the data. So, we first need to understand how many order of ARMA processes should be included. Graphical procedures can be used like plotting the data over time and plotting the ACF and PACF to determine the most appropriate specification. So, understandably, while considering AR model we should go for PACF, and while considering AMA model we should go for ACF, because that is going to only tell us where the data is going to be truncated. Otherwise, for AR model ACFs would be monotonically decreasing, and for AMA models PACF would be monotonically decreasing. Identification of models, that is selection of lag length, is done using information criteria as well. So, the alternative procedure is to go for certain information criteria. Information criteria embody 2 factors: a term which is a function of the residual sum of squares RSS, and some penalty for the loss of degrees of freedom from adding extra parameters. So, adding a new variable or an additional lag to a model will have 2 competing effects on the information criteria. The residual sum of square or RSS will fall. We know that with inclusion of additional variables, ESS or explained sum of square inevitably increase and RSS inevitably decrease, but the value of the penalty term will increase. So, it will actually offset the decrease in the residual sum of square. So, what matters is that the objective is to choose the number of parameters which minimizes the value of information criteria. So, adding an extra term will reduce the value of the criteria only if the fall in the residual sum of square is sufficient to more than outweigh increased value of the penalty term. So, if increase in penalty is actually offset by decrease in the RSS, then the overall value of the criteria will decline, right, and we will try to choose the criteria with the minimum value. There are several different criteria which vary according to how stiff the penalty term is. So, the RSS component remains roughly the same. What varies across different criteria are basically the penalty term. Now, the 3 most popular information criteria are, first of all, Akaike's information criteria that was suggested in 1974, Schwartz-Bayesian information criteria SBIC, and finally, the Hannan-Quinn criteria HQIC. These 3 I am going to discuss here very briefly. That does not mean that other criteria available or suggested in the literature are actually inferior to this or not, or it is not that it is not valid. The formula for AIC, SBC and HQIC are given below, where the logarithm of sigma hat square measures the estimated RSS from the regression as it is the residual variance. So, you know that sigma hat square is the residual variance, residual is UT hat which is obtained from a regression, and its variance is given by sigma hat square, and logarithm of it is there in all the information criteria. So, this is actually presenting the RSS part. The second term is actually the penalty term, and that varies across criteria. So, this rises with increase in k, the number of lag terms relative to the total number of observations t. So, the moment we have more and more lags included, which implies that the number of independent variables increase. So, k is going to go up, the numerator is going up, the denominator remains constant, right. Here also the denominator and a part of the numerator remains constant, but a part of the numerator increases. So, these terms are expected to increase with increase in the number of lags included in a regression. Now, if this acts as a penalty term, because this is going to decrease inevitably. So, if this fall is outweighed by this increase, then overall the criteria value increases, otherwise it decreases. We should go for the minimum value of the criteria, that is by comparing alternative models, we should go for the value of the criteria which gives us the minimum value. So, for example, I estimate ARMA models with 1 that is 1 lags, then 2 lags, then 5 lags, and then compute AIC values for each and every model, or I can go for also SBIC or HQIC, any criteria I consider, and I will basically choose that AIC value which is minimum, right, between all these models. So, that is it, that is how the criterion or the criteria are actually used. Now, here k is the total number of parameters estimated or variables considered, lag lengths considered. So, this is equals to p plus q plus 1, and t is the number of observations. Between the criteria mentioned, SBIC is strongly consistent but inefficient, and AIC is not consistent but is generally more efficient. What does it mean? This means that SBIC will asymptotically deliver the correct model order. That is, if we work with large sample, then SBIC is more consistent in the sense that this is strongly consistent, that it gives us more correct model or correct model order, while AIC will deliver on average too large a model, specifically relative to SBIC, even with an infinite amount of data. So, this has no asymptotic property, regardless of whether you are working with a small data or a large data, AIC is going to deliver a relatively larger model compared to SBIC. On the other hand, the average variation in selected model orders from different samples within a given population will be greater in the context of SBIC than AIC, because we have mentioned that AIC is more efficient. So, the variations in the model suggested by AIC is less when we repeatedly go for samples from the same population, while the variations in SBIC would be high. So, if we are working with large sample, then it is always preferable to go for SBIC. Overall, then no criteria is definitely superior to others, all of them are having disadvantages and advantages, and we have compared the two extreme cases SBIC and AIC, HQIC lies in between. Then talking about step 2, this involves estimation of the parameters of the model specified in step 1. This can be done using least squares or another technique known as maximum likelihood depending on the model. In step 3, we go for model checking, that is determining whether the model specified and estimated is adequate or not. Box-Jenkins suggested two methods, first of all overfitting and then residual diagnostics. Overfitting involves deliberately fitting a larger model than that required to capture the dynamics of the data as identified in stage 1. If the model specified at step 1 is adequate, any extra terms added to the ARMA model would be insignificant. On the other hand, residual diagnostics imply checking the residuals for evidence of linear dependence, which if present would suggest that the model originally specified was inadequate to capture the features of the data. So, residual diagnostics actually check for the characteristics of the residuals, and if the residuals are well behaved, then we go ahead with the estimation, or we think that the model is adequate, otherwise it is not. ARMA models, as suggested by Box-Jenkins approach, actually constitute a large part of statistical time series analysis. We have very briefly just presented a sketch here just to give you some idea about it. It is not even closer to the the actual analysis that is suggested and presented by Box-Jenkins. These are the references that I had followed, and this completes the discussion on AR, AMA and ARMA models. Thank you.